Hello people, welcome back to my channel. So I'm making a video after a long time. So in today's video, we'll be seeing what are linear learning machines. So we all know that in machine learning we have something called as support vector machine, then linear regression and many other linear classifiers. So this term, that is the linear learning machines, might be something new that you might have not come across, because this is moreover a generalized term for support vector machines. So we'll get into the deep dive of what the linear learning machines are. So let's start from the breakdown. So first of all, what are learning machines? So learning machine is something which takes or which makes a hypothesis, of linear combination of its input variables. Say you have x and it ranges from x1 to xn, okay, and it belongs to some set, and after this it will have some constant on the y-intercept, and it essentially will make some classification, probably in 2 dimensions, something like this, where you have all the positive and negative instances which will be very much separated. And essentially very important caveat in this is that you need to find this data points or which are very close to this line or this particular fit. So that essentially is a very important step when we deal with support vector machines. But linear learning machines are more of a generalized concept of support vector machines. So this particular line will decide how well your particular hypothesis is able to classify your instances present in the data set. So this essentially is a linear learning machine. That is simple. So that is nothing but a binary classifier. That is the general idea. So in 2 dimension, like you see in this board, it looks like a simple line, and in a 3 dimension it will look something like a hyperplane where you have x, y and z axis. So that's about the linear learning machine. So when we write the equation, so that is moreover like a linear regression equation. So you have y is equal to mx plus b, and when you just elaborate, that is m1 x1 plus m2 x2 plus m3 x3 and up till so on mn xn plus b. So how do you essentially represent this? Because this is a very well expanded form. So if you know, this is the element wise multiplication that you do with the help of the slope as well as the input vectors. So in a more generalized way, how you can represent this is in x dot b and say some constant you have c, or instead here with this example you can have mx plus b here. So this remains constant throughout all the problems that we'll solve, but essentially this thing is of the interest. So we are interested in knowing what our inner product is. So this is our inner dot product. So, and one peculiarity of this is that it is scalar, so you can multiply these things and you will get a particular quantity. So that defines how well your hyperplane or whatever your line is, it can be put into the space or the feature space. So that essentially is a main important step that you learn in the linear learning machines. That is a linear combination of your input variables, and it is represented in a inner product. So with the help of this, what you have is which you see in this angular brackets, these are the essential components that you need to have. And so you can formulate any equation, that is, if you have this particular equation which linearly separates or which does a binary classification. So if that input is greater than or equal to 0, then say if you have 2 classes, or in this case you have plus and minus. So if it's greater than equal to 0, it belongs to the positive class, or the otherwise, it will belong to the negative class. So it is as simple as that. So this is the linear learning machine, and there is one more part for this, that is something called as the dual representation. So dual representation is one more important concept, especially in mathematics, where you have a large feature space, but you cannot take the entire feature space into account, but you take a subset of this and then you apply for operations. So let me give you one example. Say you have some population, or say some set of operations, a group of operations are there. So now this group of operations, since we are learning on a binary classifier, will take a set of binary operations. Now what are binary operations? So binary operations are basic linear algebra stuffs. You know this from your high school. So that is nothing but the simple addition or the subtraction, the multiplication and the division, or the modulo operator. So something like x plus y, x minus y, x dot y, x modulo y. So where you have two operands by mean x and y, and there is one operator, that is plus, minus, dot and modulo. So these are a set of binary operations, and now with the help of this thing, so say you have a population something like this, and you have all these operators. There will be many operators in the computer, and the thing is, you want to construct a linear classifier. So let's say represent that with the help of a simple row, and now this will take the form that is G inverse. Okay, so now this particular linear function is of the form that it takes the binary operator and it takes the transpose. So what duality says is, like, if you just take the transpose of this, it will be G, which belongs, or it will have all the individual elements, that is individual. So say this is G1, G2, G3 and G4. So it will have all the elements, but the thing is, the important takeaway from this dual representation is that it is transpose of this. So you can easily transpose this entire function. So let's say tomorrow, if in your data set, or if you want to classify using some XYZ algorithm, say you want to use SVM, and if you have many number of features, but it's very impractical to store everything on your memory, because if that is in an online streaming manner, you cannot store it in a disk or in your computer. So that's where this particular principle comes into picture. So this is from mathematics. There is a lot about this thing to read. You can basically Google this and start looking at the equations. It's very scary. So just the only part that we are interested, we are just talking about that is a dual representation. So why do we write this? Because in this, essentially, if you look at this, we only are interested in having the input variables, that is what is essential, which is there in the angular brackets. So say suppose if tomorrow if you have 500 features, and if you are only computing 100 features, but that is representative of the entire population, and you can easily transpose this and you can get the work done. So essentially here what you can achieve is, if you are implementing this dual representation in SVM, you can basically apply something called as a kernel trick. So SVM is all about kernels, right? So you can apply a kernel trick there, and behind the hood, the mathematics or whatever algorithms or algebra it's making use of is probably with the help of this dual representation. So that's where this comes into picture. So now how does linear learning machines and SVM relate? So say suppose you have this linear learning machine. So this is a box. So this is an abstract concept. You add certain kernels in this, which are essential for SVM to work. The output it would produce would be SVM. So now I can say that SVM is a subset of linear learning machines. So linear learning machines is a very big class of many such linear classifiers, probably binary classifiers. So SVM is one such where you input some amount of kernels in that, or a concept of kernel will be there, and then you derived SVM out of this. So well, that was all regarding a small concept about the linear learning machines in machine learning. So hope you guys enjoyed this video. If you found you got edgy watching this video, please do like, share, comment, and if you are new to this channel, please consider subscribing. Thank you very much for watching this video.